Welcome to the DeviceDojo. This is the anniversary episode, I would say, the 10th one, finally. I'm Joseph, and this is where we tackle the practical side of securing connected devices, from over-the-air updates and fleet management to the broader challenges like incident detections and response, compliance, encryption, more, and always actionable and hands-on, brought to you by Northern Tech, the makers of Mendra.io. Yeah, it's hot here, so we're gonna take a really short episode to wrap this one up, and I'm already preparing the next batch, and I'll tell you what that will be in the end. What are we going to talk about today? I said input sanitation and validation. That sounds super familiar to everybody who has ever written a program, because people type in something. People need to configure things, whatever. And when we're talking about connected devices, it's actually a little bit more complicated, because those devices, they really ingest and load a lot of data. Some of it is super obvious, especially when a web interface is involved. This is a screenshot of the demo I'm gonna show you later, where people can enter something. This is very common in devices, for example, to give them a name. But there's a lot of other data, and it's actually probably the majority that those devices act on, which is coming from completely non-human sources, like sensor data, or reading something out of a settings file, settings storage. There's stuff that comes out of physical user interfaces. There's buttons, there's wheels, there's potentiometers where you can set some value, whatever. And there's also storage, like USB sticks. Some of these devices, for example, allow logging process data to an SD card. SD cards are cheap. SD cards are easy to handle, so a lot of people use them in the field. You just slap them in. You expect the device to write everything down. The problem is SD cards have a file format, obviously, and whenever a tool, a connected device, wants to open an SD card, it needs to read the file system. And this means ingesting data. So this definitely wouldn't be the first device which is attacked by a malicious file system, because those tools are often not as robust as you think. If we take this one step further, you can even consider everything which can be touched as malicious data. An example is you have EEPROM storage somewhere on your device. Even if you think the values in there must be good, if somebody really wants to hijack your device, they just pull off the EEPROM and solder botch wires to it, and immediately they can inject basically everything. So it really depends on how your device can be accessed, how it can be touched, and what you want to defend against. If you say, hey, I only want to defend about malicious user input, that's one thing. If you want to say, hey, I want to defend about somebody who is able to touch the device, okay. If I want to defend about somebody who can maybe even manipulate sensor data, that's a whole different story. And you need to be aware that all of this can be important. The one thing that basically nobody is ready to or is willing to accept is that when we're talking about bare metal and RTOS, and especially closed source RTOSs, then in my experience, the stack is a lot less robust than you actually think. because there's people who will sell you like this all-in-one MCU development environment, and it gives you a TCP stack. Yay! It gives you an HTTP server. Yay! It gives you whatever. But do you actually know if that stuff is good? Probably not. I just cooked up one of the ones that I could easily find, like within 30 seconds on the internet. This is a closed TCP/IP stack, which is used in such products. If you trust on this and you just say, hey, this is coming from a vendor, well, yeah, then welcome of your devices to the millions of other vulnerable ones, because nobody inspects that stuff. Everybody just trusts it. I'm not saying that everything which is happening in open source is always inspected. Definitely not. But I'd say, especially when it comes to the die-hard stuff like a networking stack or the scheduler, I'd say that stuff is pretty robust, especially when it comes to Linux, because that stuff is under super heavy load and super heavy security review. It's really hard to find problems in there. For your commercial bundled MCU IDE, I'd say that's probably quite easy. The next problem with those small devices is that a lot of the convenience functions and handling which you can expect on a higher level system is just not available. If you're doing a connected device which runs a web interface, maybe provided through Node.js, then you can easily find a library which says, hey, okay, this is the input that is coming from the web, either posted by the UI or coming through a REST API or whatever. Make sure that this is not malicious. Sanitize it. Make sure all bounds are kept, and so on and so on, and only then proceed. You just have to remember it. If you're going, I've found one for you, for example, for Golang, the validator thing. But this stuff exists for basically everything. For Golang, for Node, for TypeScript, for PHP, for Python. You can easily have it. If you're programming for an MCU, not so much. You often have to first remember it, and then you do it yourself, and then you probably botch it. If you ever want to be really scared, then look up how to check if an email address is actually valid. It's a lot more complex than you will think. Additionally, I just hinted at file system drivers. This is what I meant. If you're using a Linux device and you're just giving it a file system, it will do all kinds of checks and say, hey, this file system is broken. Do you want me to fix it? Do you want me to just ignore it? Tell me. And then it will say, hey, I'm good. I'm safe. This just doesn't work. Whereas on your MCU, with your maybe hand-carved file system driver, and yes, I've been there, yeah, what do you want to do? Do you even think about this being a problem? So the challenge here is either stuff is not available or it is often very, very lacking. And this decision, if something is dangerous, if something is malicious input, is actually not that simple. Because what do you want to arm for? Buffer overflows, yeah, we've already heard about that. But this case, for example, HTML. User input in a web field. Okay. To set the name of your device. Okay. Developers don't think that somebody could possibly enter SQL there or HTML code. So what do you check for? So this is an example of a very, very, very simple attempt to sanitize HTML inputs. And I'd say if you're doing a web interface on an MCU, this is the absolute minimum that you need to have there. But as I said, it's not only malicious data. It can also be what I called here stupid data. If you're reading something from a sensor, sensors usually are calibrated within a specific temperature range, like minus 20 degrees to 200 degrees. That's a common range. And something comes from that sensor. Is it within that range? Maybe yes, maybe no. Did it change super fast? Maybe yes, maybe no. And what do you want to do with that if your data looks wrong? Do you want to just discard it and carry on? Do you want to say, okay, I'm going to drop one, but if the next one is broken? And it's often not that easy to see where something is going wrong. If the input is just coming wrong from the sensor, if you're having like an attack, if you're just having something badly happening to the sensor, if you're having somebody tinkering with the wires, if there's a glitch in it because somebody put your old DECT telephone on the device, you don't know. In many cases, the line between what is an attack and what could be just legit but bad input is super, super blurry. And when we're talking about such devices, then you have the additional problem of what do you want to do if you detect that there is bad input? If it is something related to a user input, then it's easy because then you know that the user is actually at this very moment touching the device. They do something, it's probably you detect there's a problem with it, you tell them, hey, something's going wrong here. That's easy. Now, when you're basically doing an HVAC, for example, and there's this temperature sensor outside of your building, you're seeing bad data there. What do you do about it? Ignore one, ignore two, ignore an hour. When do you want to raise an error? Is it maybe somebody trying to trick you into something? Do you want to tell your users that your sensor is showing glitches? They say, the only thing I want to have that is that it's warm in my home. They say, I don't care. Probably they don't even realize that something is blinking down there. And so the challenge of acting on bad data in a simple connected device is very, very hard. And I'm not making this up. This can be an attack, just maybe not on the thing that you thought. Just as an example, there's bets on temperature. At the Paris airport, there was a bet on at which temperature a specific meteorological station would be at a specific point in time. What could possibly go wrong? Yes, somebody could take a hairdryer. So now, my question is, would there have been a chance to understand that this is actually invalid input? Because weather data does not change that fast, right? You have your temperature sensor outside. Somebody who is competent in that field makes sure it is shaded. So what's the possible maximum gradient that you can see there? I don't know, but probably a couple of degrees Celsius or Kelvin per hour. Now, if somebody goes near it with a hairdryer or a torch, a lighter, something, it would move a lot faster. So there could have been signs of a gradient that this is an attack. We're coming back to what I just told you. How do you want to react on it? And that's what I mean with basically everything that comes into a device can be malicious data, even if it's just a simple temperature sensor. A lot of explanations, so it's really time for the demo. Remove this and get that. I'm using a very, can you see this? Cable's too short. Yeah, bad planning on my end. Come on over here. So this is a Raspberry Pi Pico W2, and it's running a super simple web server. Like said, in many cases, you would give those devices a name. It would be stored somewhere, and when you next log into the device, it would just cram out that same string again and say, "Hey, I'm the device Office 1, whatever." In this demo, we're just using name and hello. My name is Office 1. Let's stick with that one. Office 1. I can greet, and it says, "Yeah, hey, hello, Office 1. Awesome. Everything's working." Now, what would happen if I put HTML in there? Boop. Whoa. That's not my name, right? That is actual code injection. And the point that I'm trying to get across is that code injection is not only something which happens on big servers or on your favorite website or somewhere else. It is something which actually happens even on those small devices. And I'm just gonna turn on my sanitation here. Boop. And you can see now it understands that there's something wrong, probably. And it says, okay, I'm just gonna make sure that this string is parsed and used, but not just being spewed out again. And I think this is a nice example of places where you can think that something is should be like treated carefully. With that, I think we even ran longer than I thought. Too much bubbling, too much explanations. Hopefully, you could take something away from it. Yeah, if you want to know more, you can always find us on Hubman.io to discuss all of this. And like I said, the stuff that I want you to take away is whatever input your device sees, always think about it. Is this really sensible? Like settings in your EEPROM, especially free text input fields from whatever source, over UART, over Web UI, over Canvas. It really doesn't matter. If it contains text, it is suspicious. Measurements. Are they glitches? Are they attacks? Does somebody want to trick you into something? I don't know. You have to think about it. And especially whatever comes through an SD card or whatever kind of storage. All of this stuff is hard to get right, and especially on MCUs, because you can't trust the operating system, the Linux kernel, to do things right. That's the big lesson here. And as promised, this wraps up the first batch of 10 DeviceDojo sessions. Thanks for hanging in with me. And in the next batch, I'll finally get to cryptographic stuff. I've shied away a bit from it because I really want to do it right, but I think it's time now. So we'll start out session number 11 on August 13th with signatures. What is it? What does it tell you? How do you create it? How do you check it? Especially on connected devices. And that's it for today's DeviceDojo. Hit subscribe if you don't want to miss the next session, and drop your comments, whether you've got questions about what we covered or ideas for future episode. I always love to hear from you.
And if you're ready to implement professional OTA updates in your own projects, always check out Mender.io with a lot more stuff here now, by the way. And all the links are in the description. Hopefully see you around in the next episode. Bye.